How does the change in mass of the cart affect the acceleration when the net force is constant?
Our question addresses how the change in the cart mass affects the acceleration when the net force is constant. The cart will be pulled by the pulley system on a nearly frictionless dynamic track, therefore the cart can have a continuous motion. The hanging mass will be the same, so it will have a constant net force that will pull the cart for different trials. This experiment will explain the relationship between the weight of an object being pulled by the same net force. Our claim is that the acceleration will gradually decrease when the cart mass is increased.
The mass of the cart, the independent variable, is being changed with the weight we place on the cart. In this case, the hanging mass, the dependent variable, is kept constant. The procedure is as followed. Step 1. Have one end of the string attached to the cart and the other to the hanging mass weighing 100 grams. Step 2. To set up the pulley system, place the cart on the flat portion of the track and pass the string through the pulley, leaving the end of the string with the mass hanging on the opposite side. Step 3. Set up the motion tracking program, PASCO, and position the motion sensor so that it is at the beginning of the track facing the cart. Step 4. Connect the motion tracker to the computer to analyze the change in speed. Step 5. Hold the cart until the string is parallel to the surface. Step 6. Pull the cart back. Step 7. Release the cart while pressing start on the motion tracking program. Step 8. Calculate the acceleration when the cart is moving. Step 9. Repeat steps 1 through 6 with a series of larger weights on the cart while the hanging mass, which is the net force, remains the same.
In conclusion, the results we acquired supported our claim, which is that if the cart's mass is increased, then the acceleration will decrease. The cart's mass versus the average acceleration graph shows the theoretical values, blue line, experimental values, red line, and the exponential trend line. The data does support our claim, since the acceleration decreases when the mass is increased. To find the theoretical values of the acceleration, we use the equation the acceleration of the cart is equal to the hanging mass times gravity plus the frictional force divided by the hanging mass plus the cart mass. We assume the frictional force is 0 newtons because the track is supposedly frictionless. However, our graph is inaccurate. Both the theoretical and experimental lines are parallel and nowhere near each other. If the coefficient of friction between the track and the wheels was determined, that could have given us a more precise database instead of assuming frictional force is 0 newtons. Some errors we encountered were both systematic and human errors, which included the string's inability to hold the weight securely, the sensor not detecting the cart, and the weights on the cart not remaining stable. These problems were resolved by securing and straightening the cart as best as we could, and that the weights were within the center of the cart. The sensor was pointed directly at the cart for more accurate data. Some ideas for future investigations are experimenting with different wheels, changing the surface of the track, and using different types of strings to see if the acceleration would change.